Next, we're going to look at two alternate methods for computing the area under the curve of the graph of a given function. So suppose we have a function, so here's the x-axis, and we have some function like this, y is equal to f of x. So we previously saw how we can use certain types of Riemann sums to approximate the area under the curve between x is equal to a and x is equal to b. So we had the right-hand Riemann sum, the left-hand Riemann sum. So the idea was we divided the interval from a to b into slices, and then we approximated the height of the function using either the right endpoint of each subinterval or the left endpoint of each subinterval. In particular, we had delta x was b minus a over n, and then x sub I is a plus I delta x, and then x sub I star was some point between xi minus 1 and xi. And so our general Riemann sum with n subintervals was the sum I equals 1 to n of f of x sub I star times delta x. So this is the height of the particular individual rectangle, and then this is the width of that rectangle. Now, for the special case of a left-hand Riemann sum, so we call this LHN, we get the sum I equals 1 to n of f x I minus 1 times delta x. So xi minus 1 is the left endpoint of the ith subinterval. And for a right-hand Riemann sum, we had the sum I equals 1 to n of f of x sub I times delta x. And x sub I is the right endpoint of the ith subinterval. So if we use just the left endpoints of each subinterval to approximate the height, so I would use this height for the first, this one for the second, that one for the third, this one for the fourth, that one to the fifth, I get the left-hand Riemann sum. If I use the right endpoints, so this one for the first, this one for the second, this one for the third, that one for the fourth, this one for the fifth, I get a right-hand Riemann sum. Next, we're going to look at two alternate ways for approximating the area. The first one is a new type of Riemann sum called the midpoint rule. So the midpoint rule says for x sub I star, so this is the point that we're using for our Riemann sum, we use x sub I plus x sub I minus 1 over 2. Now, in other words, if we have x sub I minus 1 and x sub I, it's the average value of those two x values, which is the point exactly in between. So here is the point, so here's the estimation point used, so the point used for the midpoint rule. So if you use the exact center point to approximate the height of the rectangle, so for the first interval, I'm going to choose the point right in the middle. And I'm going to evaluate the function at this point and use that height. It's the middle point. The middle point here is going to be up here, so I'm going to use this one for the second one. The middle point on this one is right here. The middle point here is right about here. And then the middle point here is right about there. So I'm going to use the middle values for the heights of the individual rectangles. It's a little bit slanted to the left, but you get the idea. So that would be a graphical representation of the midpoint rule. So this is a visualization of what the midpoint rule would look like. So it's literally the area of those 5 rectangles right there. So if you want to come up with an actual formula, you could say the following. You could say the midpoint rule with n subintervals is the sum I equals 1 to n f of x sub I minus 1 plus x sub I over 2 times delta x. But the key point here is that this is just the midpoint. So this is the midpoint of the ith subinterval. It's the point right in the middle. It's right between the left hand and the right hand sum. So that's what you do for the midpoint rule. So sometimes just remembering that and using common sense in the table you don't have to necessarily apply the formulas each time. You know what the midpoint is, so you know to use that point to approximate the function f of x. Now, if we have a function that's concave down, so let's say we have this concave down function, I'm going to divide it into a couple given pieces. Now, I don't want to prejudice myself about whether or not this is increasing or decreasing. I just want it to be concave down. So parts of it are concave down and increasing, and parts of it are concave down and decreasing. Now, if I use the midpoint rule, like this, so I'm getting the following estimates. Like that. So using the midpoint rule, part of the estimate's going to be over the curve and part of it's going to be under the curve. So let's look at this a little bit more carefully. So let's say we have a concave down function and we're estimating this with the midpoint like that. Now, concave down means that the slope is decreasing. So the slope is increasing greater over here, or it means that the slope is increasing at a smaller and smaller rate or decreasing at a greater and greater rate. So the slope's increasing here, but it's increasing at a smaller and smaller rate. So the area here, so if we look at the difference, the missing area, so let's do red for area outside of the graph. So that's extra area, and then green for area inside the graph. It's not included. The question is, well, which one's going to be greater? And the answer is that the red area will always be greater than the green area if you have a concave down function. And the reason is because if you're exactly in the middle, and you know that the rate of change is greater up here, so it's actually starting at a lower point and then leveling off. So it's the same delta x over 2. So this one here is delta x over 2 because it's half of the width, and then this one is also delta x over 2. But since the rate of change is less over here, it's not going to get as much area outside of the rectangle. So there's more area that was included that wasn't a part than that wasn't included that is supposed to be there. So the whole idea is that the true area, so if a function is concave down, then the true area, so let's see, the true area is going to be this one. So is the true area less than, the true area is going to be less than or equal to what you get from the midpoint rule. So hopefully this kind of argument can, and it's easiest at the very top because the midpoint is going to definitely be an overestimate for the actual area. But hopefully this argument here where you're increasing at a greater rate and then the rate that you're increasing is less, so you're going to capture less area to the right of the midpoint than you miss, or you're going to miss less area to the right of the endpoint than the extra area that you capture to the left. And then the opposite's true when you're decreasing. So you're still going to end up with more area that's not supposed to be there than that you're missing area that is supposed to be there. So we'll talk about this in a little bit again. But now the next method is the trapezoid rule. So here, let's divide this up into slices again. So we have a graph of a function, just like that. So here's A and here's B. Here's the x-axis. Here's the y-axis, and here's y is equal to f of x. So the trapezoid rule is actually not a Riemann sum per se. So instead of using rectangles, the idea is to, for each individual strip, we look at the two endpoints and we form a trapezoid like this. We look at these two endpoints and we do a trapezoid like that. These two endpoints, we have a trapezoid here. These 2 points, trapezoid like this. Those two endpoints, trapezoid like that. So the area, the approximation is going to be the area under the trapezoid. Already, the approximation looks pretty good because you're only missing the portion of the curve that's non-linear. So if you had a line connecting the two endpoints, you're going to get the exact answer. And so really for your thin little subinterval, you're only missing out or gaining extra of how the function deviates from a line. So you're only looking at the second order perturbations from its linearization. So the trapezoid rule for the ith trapezoid, what is the area under a trapezoid? Well, we're going to get delta x and then times f of x sub I plus f of x I minus 1 over 2. Right? So this is the average of the height here and the height here, because when we have a trapezoid with two different heights, the area of the trapezoid is just the average of this height and that height, because if I average those two heights together and made a rectangle with that height, I would get exactly the same area. Since it's a trapezoid, there's an equal area here as there is there. So this piece matches exactly with that piece. So this is the ith term for the trapezoid rule, and we can compare this to the midpoint. So the ith term for the midpoint rule was delta x times f of x sub I plus x sub I minus 1 over 2. So you can kind of see the difference. In the midpoint rule, we're averaging the x values. So we're taking the average x value, and we're going right in the middle, and we're evaluating the function at that average x value. For the trapezoid rule, we're taking the outputs at the left endpoint and the right endpoint and averaging them together. So the trapezoid rule, we would sum up all of these, and the midpoint rule, we sum up all of those. So it's a matter whether you average the two endpoints in x to find the center point and then evaluate the function at the center point. That's how you do the midpoint rule. Or whether you just evaluate the function at the left endpoint, evaluate the function at the right endpoint, and then average those two together to get the area of the trapezoid. So that would be the trapezoid rule. Now, an additional note that if you have the trapezoid rule with n subintervals, that's going to be the sum I equals 1 to n of f of x sub I plus f of x sub I minus 1 over 2 times delta x. Now delta x and 2 are the same, so we can manipulate this, and we can write this, and there's a sum here, so we can pull out the sum and distribute the delta x. So we can write this as 1/2 of the sum I equals 1 to n of f of x sub I delta x plus sum I equals 1 to n f of x sub I minus 1 delta x, like that. So if you just break apart the sum, you can rewrite it like this. But this is just 1/2 of the right-hand Riemann sum plus the left-hand Riemann sum. So what we find is that the trapezoid rule, if you already have computed the right-hand and the left-hand Riemann sum, you can average those two Riemann sums and you get to the trapezoid rule. So the trapezoid rule is really just the average of the right-hand sum and the left-hand sum. So you take your left-hand Riemann sum and your right-hand Riemann sum, average them together, you get the trapezoid rule. Now if you have the trapezoid rule, and suppose we have a concave down function, so these ones are supposed to be the lines. So if you approximate this concave down function using trapezoids, you'll notice that the trapezoids always are less than the curve. So for a concave down function, the trapezoid rule is always less than or equal to the actual area. And we said that the area was less than or equal to the midpoint rule. So the trapezoid and midpoint rule present lower and upper bounds, respectively, for concave down functions. Now, in the converse, if you have a concave up function like this, the trapezoids are always going to give you more area than that lies underneath the curve. Notice that the trapezoid area is greater than the area under the curve. So for concave up functions, it's just the opposite. So the midpoint rule is going to be less than or equal to the area, since it's going to be less than or equal to the trapezoid rule. So the overall summary, if your function is concave down, then the trapezoid rule, so you can always think, okay, concave down, trapezoid ones are going to be like this. Okay, those are underestimates, less than or equal to the area, less than or equal to the midpoint rule. If it's concave up, the midpoint rule is going to be less than or equal to the area and less than or equal to the trapezoid rule. So that's how the trapezoid rule and midpoint rule become upper and lower bounds when you have concave up and concave down function. So they play an analogous role to increasing and decreasing functions and the left-hand and right-hand Riemann sum. So we recall that if a function is either increasing or decreasing, the left or right-hand Riemann sum, one will be an upper and the other a lower estimate, and then the opposite with the case of decreasing functions. So increasing and decreasing, the left and right-hand Riemann sum, and how to remember that? Okay, left hand increasing, the left hand is going to be less. So for an increasing function, the left-hand Riemann sum is less than or equal to the area, less than or equal to the right-hand Riemann sum. And for a decreasing, it's the opposite. Decreasing right-hand Riemann sum, less than or equal to the area, less than or equal to the left-hand Riemann sum. So depending on if you have an increasing function or a decreasing function, the left or right-hand Riemann sum provide upper or lower estimates to the area. And then similarly, if you have a concave up or a concave down function, the trapezoid and midpoint rule provide the upper and lower estimates for the actual area. And I think the trapezoid rule one's pretty obvious. If you have something that's concave up and you're using trapezoids to approximate that, clearly you're capturing more area than is under the curve. Midpoint rule is kind of obvious in the center point, because if you look at the midpoint, that's going to be an overestimate for concave down. So concave down, midpoint, overestimate. Concave up, if you look at the center point, concave up, the midpoint rule gives you the underestimate, and the trapezoid rule, which would be here, gives you the overestimate.